Okie doke. So, what have we learned? So, can we actually apply this model to empirical cases? If you look at the paper, you'll see that we can. Okay, we don't have to assume this very restrictive form of the stock. We can assume different shapes for the stock. We don't have to, of course, we don't have to interpret the depth. Literally, we can think of depth as grade also, for instance. So there's typically two problems with resource extraction. One is increasing depth, another is decreasing grade, where grade is the percentage of the resource per ton of, in each ton of material. And for a lot of resources like copper, for instance, which is discussed in the paper, it's the grade, both the grade and the depth are worsening over time. We extract the stuff near the surface with a high proportion of copper, initially up to 10%, and now we're down to less than 1% anyway on copper. And we can adapt this model and actually model empirical cases and make predictions about when prices are going to start going up. It's reasonable to expect we're going to move towards something more like that intermediate balanced growth phase with increasing prices over the next couple of 100 years. Which makes a lot of sense because we're still only scratching the surface. I mean, the Earth's crust is a big place, but if we keep increasing resource extraction by 3% a year, roughly, which is what's been happening for the last 100 years or so, then it's not going to be long before, again, few hundred years, 100, 200 years, you're soon up in absolutely phenomenal extraction rates. And of course, then we would expect the price to go up, either because of the increasing depth, decreasing grade, but also potentially because of competition for land. Okie doke. Let's see. So that was empirical application. Does the model help us understand patterns? Well, I would say so. Why do resource prices often trend downwards, especially historically? It's these growth rates, right? That theta AX is empirically often higher than theta AY. So the productivity of extraction inputs can grow faster than their price, like the wage. Productivity of extraction labor with capital grows faster than the price of hiring that labor and capital. So then unit costs go down. What's left out of the model? Well, a lot of different things. So one thing you might think of is market power, of course. But another thing, which I'm going to talk about a bit in the rest of this video, or quite a bit of this video, is the demand side. Okay, we have this. We've zoomed in on extraction and we've ignored all the complications about demand. Maybe there's substitute resources which could also be demanded. Maybe we can economize on the resource. Maybe we can shift out of resource intensive sectors if the price of a particular resource goes up, and so on. So we can have a quick look at that. At demand. Okay. So what does the model teach us? We can solve problems related to resource stocks, extraction costs, predictions about the price. But what about the resource demand and the Cobb-Douglas production function? So that production function I'm talking about is here, which determines how demand for this resource develops. And this is related to criticism of the sort of DHSS model going way back by ecological economists like Daly in the Solow-Stiglitz variant. To make a cake, that's the final good, we need not only the cook and his kitchen, but also some non-zero amount of flour, sugar, eggs, etc. This seems like a great step forward until we realized we could make our cake 1,000 times bigger with no extra ingredients if we would stir faster and use bigger bowls and ovens. So, trying to get just a clean picture here. If this is the cake, if this falls, well, if AL grows, or if we put in some capital here and let capital grow, that's the bigger bowls and ovens, we can still maintain the flow according to this. Does this make sense? Well, not for cake, but we have to remember that this flow of goods is an overall aggregate of all the goods, and there's all sorts of substitution possibilities and so on. Cake is very dependent on particular inputs. Food in general is quite a special case, right? A lot of other products, we can imagine how technological progress can allow us to produce more and more value without the physical inputs. But we should model that, right? That's just speculation. We want to actually have models of that. We want to model the demand side. Okay. So how can we save on flour, sugar, and eggs? We could reduce waste. We could make the cakes more efficiently. It's quite tricky with cakes, but with lots of other products, we can imagine that the potential is great. We could use other inputs, or we could shift on the demand side. We could have composition effects and shift out of cake, so we can still have economic growth even if we don't increase our cake consumption, because we can increase consumption of other stuff. So there's various mechanisms: resource efficiency, switching inputs, changing consumption patterns, that we're sort of abstracting from in this model and just saying, like, from this bird's eye view, it looks like a Cobb-Douglas, and it sort of fits the data, right? Because the Cobb-Douglas, the data shows a constant factor share for energy and resources over time, more or less, which is what you get out of a Cobb-Douglas. But what's behind that? It's some or all of these processes. And to really feel confident about what's going on and what will happen in the long run, we need to delve into these processes and understand them better. Because just because it's worked so far doesn't mean it's going to carry on working. Okay, and we're back to that Solow 1973 paper. But actually, what we've seen in the data for resource use is more these processes in reverse. Because resources haven't got more expensive, we haven't developed resource efficient technology, we haven't substituted to other things, and we haven't shifted our consumption away from resource intensive goods. That explains why the consumption has grown. But if the resource prices really did start to rise, then these processes would kick in. And we do have lots of evidence that that does happen. For instance, after the oil shocks, when energy and resource prices did rise in the short temporarily, we see these processes happening. We see it happening at a more micro level for specific pollutants. We can't do it with the Cobb-Douglas. The Cobb-Douglas is like looking at the overall abstract. We need to delve, to unpack that Cobb-Douglas and model these processes specifically. Okay. And we'll look at how you do that later on. finally, I think, pretty much, or not quite finally, there's a big difference between energy and materials, land. So if we go right back to the workhorse, these substitutions are crucial, right? We clearly need to substitute away from these and into this. We can do that for energy. But ultimately, land, like how do you substitute for land? Okay, so ultimately, and even these renewables are dependent on land. So for energy inputs, we're going to gradually substitute to renewables, even more so when we add pollution into the equation. But land we can't substitute for. So land is like the ultimate resource in a way. Let's go back to the notes. In the very long run, substitution to alternatives becomes crucial. For energy, we'll substitute to flow resources, blah blah blah. For materials and land, the problem is not exhaustion, but how we use the fixed quantity available. Okay, so those are super interesting research questions. Finally, these non-renewable resource questions have kind of gone out of fashion. One reason for that is that it's not really obvious where the market failures are. So in the models we've talked about so far, for resource extraction, there isn't really any market failures in these models. So it's like, okay, this is all fine, so we can predict what's going to happen and so on, but do we actually need policy intervention? According to these models, we don't. But of course the models are missing, leaving a bunch of things out. If property rights are ill-defined, then you've got huge problems, right? And that is linked to a massive literature on something called the resource curse, which we're not going to talk about, but you could look at if you're interested. What about market power? We know there's huge market power in the oil sector, for instance. That makes a huge mess of things. In general, you might think if we're worried about resource exhaustion, then market power should be great, because market power leads to lower rates of extraction, you might think, and higher prices. Well, A, that's not necessarily true, and B, when you've got resources substituting for each other, if there's market power in one sector and not in another, you can end up basically screwing things up. It can create a horrendous mess and big losses. Again, we're not going to look at that in the videos, but it's something you could look at for your essay, for the essay task, if you're interested. There's another idea that the market discount rate, interest rates, if you like, in the market don't reflect social preferences. For instance, you could famously discussed by Stern in his review of climate policy from the earlier on this century, 15 years ago, I guess, the Stern review came out. So that could also be a problem if the discount rate in the economy is not the sort of socially optimal discount rate. That would tend to create too fast resource extraction in these, according to these models. Okay, and that's it for non-renewable resource extraction, and I think now it's just pollution left for my part of the course.